Welcome to a lesson with Dr. Powell. Let's talk about what an eigenspace is, what an eigenvalue is, what an eigenvector to keep these things straight. An eigenspace is a subspace of a vector space where the minimal polynomial on that subspace itself has degree 1. So there's a degree 1 polynomial of associated with a particular matrix X. So here we're kind of talking about a specific matrix. So X is going to represent a matrix here. So for a particular matrix, we have eigenspaces, and those are just subspaces where the minimal polynomial for this matrix X is degree 1. So like X minus 2, X minus 3, something like that. An eigenvalue would be like if the minimal polynomial is X minus 2, the eigenvalue would be X equals 2 for that, okay? And this basically means, so this is behaving like 0, which means that the matrix itself acts a lot like the scalar, acts exactly like the scalar 2 does on that subspace. So if you apply the matrix X to a vector, like X, V, okay, that's the same thing as saying 2 times V, all right? That's what it means on that subspace. So it's not going to work on the whole vector space, but just on part of it. All right, so that's what an eigenspace is. An eigenvector is just a vector within that eigenspace. All right, now what's all this up here? So different subspaces might have different minimal polynomials. So one subspace might have this minimal polynomial. Now necessarily, this subspace up here, as we get larger, like V is contained in W. Out of necessity, the minimal polynomial here should be a multiple of this guy, because the minimal polynomial over here, if we apply it to anything in here, is going to get 0, but anything that does that has to be a multiple of this guy. So hence we get that. Now, also realize that as we adjust the minimal polynomial and we go up, this right here, everything that has a specific minimal polynomial actually ends up being a vector space in and of itself. It's closed and everything else under the normal vector operations. So because of that, as we change the minimal polynomial and go up like this, we actually have to add dimensions. We must add dimensions that way. Linearly independent vector, compared to what we had before. If we had a basis over here, we have to extend the basis. Dependent means that you actually you're staying in the same place in the same subspace. So just kind of keep that in mind. Now, if you have P of X times Q of X is the minimal polynomial on a space W, then that means that the range of P of X is a subspace with the minimal polynomial QX, the other guy over there, all right? That's because a minimal polynomial is minimal, and the minimal thing and if we're in the range here, right? That's that means there's an input that came through it, and the minimal thing to make that 0 all the time is to have, for all vectors, is to have Q of X multiplied on to make it 0. So hence we can kind of use this idea of looking at ranges of different subspaces. This is actually a very useful technique, and we'll be seeing that in some examples here. Thanks for watching.